Good morning. Welcome back to Calc 2. Hope things are going well for you. I have a little bit to talk about from Chapter 11, Section 2. I asked you to watch a video over Section 2 where you were introduced to power series and ended up with this theorem. I have it on the board. Let's read over it. There's our power series. A formula AK that generates coefficients, and then we have x to the k. And of course, our goal here is to find all the values of x for which the series converges. And it turns out, as the previous video showed, there were three possibilities. The first one is there is a positive number r so that the series converges if the absolute value of x is less than r, that is, x is between negative r and r, and it diverges if x is bigger than r or less than negative r. And when that r exists, this is the first case, remember, we call it the radius of convergence. Another thing that can happen over here on the right, on the top, it can converge only for x equals 0. That's a super boring case. It's not really a series. There's really only one term, and that would be a sub 0. And it's not interesting. We really don't have much to say about it, but it's a possibility, so it's listed here. The third thing is actually we'll discover quite a bit. That is, it converges for all x minus infinity to plus infinity. And so if you think about radius of convergence, we would assign infinity to the value of r. So the first case, r is a positive number. The second one, it's 0, and it's a totally boring case. The third one is a very interesting case, and r is infinity. And without proving these, I've given you an example for each case. The first example over here, I'll let you work out the details. We're not going to take time on the video, but you can show, and maybe there was a homework problem pretty much like this, you can show that r equals 2. That is, that series, the first one, converges if x is between negative 2 and 2, and it diverges if it's outside of 2 or negative 2, greater than 2 or less than negative 2. You also remember on the video, there was a discussion about the interval of convergence, and those issues are still here for the first case, and we're not going to worry about it. I will tell you, I believe it diverges at both endpoints, and so we would just take all the numbers strictly between negative 2 and 2. The second one converges only at 0. That factorial growth, it kills the exponential growth, and it's a totally boring series. Third one is one of the most interesting series of all we'll discover in the next chapter. And it turns out, notice all I did was flip the factorial down to the denominator, and it changes it from r equals 0 to r equals infinity. So very interesting case. And that's where we'll start. And then I want to lead us into a few more things that are contained in Section 2 before we move on to sort of the grand finale for infinite series, Taylor series in Section 3. All right, give me a second. I'll pause this and change the board over. All right. So continuing in Section 2, here we have power series. And let's say we have an x value on the interval of convergence. So it's reasonable to think that on the interval of convergence, the power series converges to some function. And to start with, I've just called it f of x. And what we want to do is make connections between power series and the function f. And you can see for x less than r, so we're on the interval of convergence. Now, it turns out there are a couple of things we can do and preserve convergence. The first one says, as long as we're on the interval of convergence, I can differentiate the function and I can differentiate the terms of the series. Notice we've taken x to the k, we've pulled the k down, and we decreased it by 1. We're taking the derivative term by term. Of course, we know we can do that. We learned back in Chapter 3, the derivative of a sum is the sum of the derivatives. But our sums were never infinite, and that makes some technical difficulties, but they don't cause any problems here. This result says we can do it, even though it's an infinite sum. So I differentiate the function, and differentiate the series, and that gets me a new power series that converges on the interval of convergence to the derivative of the original. The interval of convergence will remain the same. I'm sorry, the radius of convergence will remain the same. It's possible we could gain or lose convergence at the endpoints. As you saw in the previous video, we always have to check the endpoints. There's no easy way. It just depends on what the series are. So the radius will stay the same when we differentiate, but the endpoints could change. We'll see. All right, the second thing we can do is integrate. So this is an antiderivative of not a definite integral. And so I integrate the function f of x, and I also notice again we're integrating term by term. We're raising the power by 1, dividing by the new power. AK is just a constant, just comes along for the ride. And because this is an indefinite integral, there's always the possibility that of a constant of integration. In most of the examples we do, that constant will turn out to be 0. We may not even think about it, but in theory, it should probably be there, the constant of integration. And now I've worked out a very important example to illustrate the first case, and then in a minute we'll do the second one. So, hope you can see that, yeah. So what I need, if I'm going to use the first category, that's we're going to differentiate. So I need to know some fact to start with, right? If I start with this, and then I can say something beyond it using this property. So I need to think, where can I start? And well, we have a super good starting point, a geometric series. I can think of a geometric series as a power series, where if I think of it as geometric, I'm thinking of r gets raised to the power k, and so we can see, if I look at that as a geometric series, my r value, the ratio we call it, is just the x value. And we know it converges because we can see the geometric form. If x is between -1 and 1, therefore the radius of convergence is 1. And we know what it converges to. The first term, when k equals 0, you plug it in, you get 1 over 1 minus r. So this is the function f that we're going to start with. So we kind of lucked out. We knew a power series. We knew what it converged to. So this guy is playing the role of f, and this guy is our power series. And then what we said over there says, okay, now we can take the derivative. So sometimes this is easier to do if I write the series out long form instead of sigma form. And so we'll write it this way. We'll do the work, and then we'll write it back in sigma form. And either way is fine. I'm not super picky about how we choose to write it. It'd be nice if we could go back and forth. So here's the fact that we know to start with. We know this from the previous chapter. One of the very first special series we looked at, the geometric series. And now this thing says we'll take the derivative. So we're going to differentiate here. We're going to differentiate there. Over here, using the chain rule, you can check my work. We get 1 over 1 minus x quantity squared, trust me. And over here, we just do it term by term because we're summing. So the derivative, oh dear. I made a mistake. I'm differentiating on the left and integrating on the right. So pause. All right, thanks for waiting. I'll fix now. Take the derivative. This is what we get on the left. That's what we get on the right. And this result over here says that that new series, the one on the right, power series, converges to the function on the left. I wrote it out long form up above, and down below I wrote it in sigma form just for the practice. Like I said before, it doesn't matter to me really. I'd like us to know how to do that, to take a long form and write it in sigma form or vice versa. But as long as we get it right, that's the main thing. And there's some flexibility here depending, you can start the series at 1 or at 0, it doesn't really matter as long as the formula cranks out the right terms. And of course, this is true, this power series converges for every x to that function as long as x is inside the radius of convergence. And the derivative series inherits the radius of convergence from the original series. So r equals 1 here. So for example, let me just show you. Let's pick a number like 2/3. inside the interval of convergence, and then we have a specific fact. So I plug 2/3 in on the function. On the left, I plugged it in. Let's look at it in this form. No, let's look at it in sigma form. So k equals 1 to infinity. K. And then I have x. Well, we're picking 2/3 to the k minus 1. Do some arithmetic here. 1 minus 2/3 is 1/3. Squared is 1/9. So 1 minus 2/3 is 1/3. 1/9. 1 divided by 1/9 is 9. This series converges to 9. Okay, a series we've never seen before. It's not a geometric series. It doesn't really have any form we can say it's this kind of a series other than just a power series. And we've been able to prove that, for the value 2/3, that the corresponding, notice this is no longer a power series. This is an ordinary series that we would have seen in the previous chapter. Remember actually in the last chapter, early on, we could find the values that series converge to. And then I said, we're going to give up on that. We're just going to decide for a while, does it converge or does it diverge? But I told you a few times, someday we're going to care again about what it converges to. And now that day is here. So we can actually in all of the last chapter, we could not find the sum of that series. We could prove it converges. The ratio test would work nicely, but we could not find what it converges to. But now we can, because we can connect it back to the geometric series. All right, I'm going to pause here and set the board up for the second kind of modification we can do. The first one was the derivative, and the second one is the antiderivative. Give me 1 second. All right, we now have an example of using the second modification, that is antiderivatives, to finding a power series and the function it converges to. So again, we start with the geometric series. And now we integrate. On the left, we get the negative log of 1 minus x. Check it out. Make sure it's true. I don't need absolute value signs because remember x is between -1 and 1. I forgot to write it here. This thing only makes sense if x is between -1 and 1. And so 1 minus x can't be negative. The minus on the outside comes from the derivative, so to speak, of the inside using the integration by substitution. And on the right, super easy. You just have a polynomial type structure. So raise the powers, divide by the new power. And then I decided to just multiply by -1 so that we could get a power series that converges to the log function. In this case, the log of 1 minus x. So I just pulled it out in front there, and you can see the form that we get, 1 over k x to the k. I had something, the constant of integration. I showed you that it was there on the last screen, the last whiteboard. I told you it was usually 0. And the way we could find is we could plug in x equals 0. Remember, every power series converges at x equals 0. And so we could balance the two sides up if by plugging in x equals 0. And if one side was 3 units bigger than the other one, then we would let C be, which plus or minus 3, whichever one it needed to be. If I plug in 0 over here, clearly I get 0. If I plug in 0 over there, I get the natural log of 1, which is also 0. So the constant of integration is 0. And like I said, it usually is 0, but we could take a quick check. Now, just like we did last time, I could write a specific series out, but I want to do something a little bit different. So here we have a power series that converges to f of x. Let's just write it out. 1 over 1 minus x equals 1 plus x squared, so on. Always qualified by, it only makes sense if x is between -1 and 1. And now I realize you couldn't see the work that I did. Let me give you a second to look it over. I guess you could hit pause and look it over for as long as you need. All right. Now, think of this guy as, you know, our f of x back in the original expression. And now what I want to do is take a look at the function f of minus x. But is I want to replace all the x's with minus x. And see if we can figure out, you know, how that's going to influence things. So on the right, on the left-hand side, if you plug in minus x for x, we're just going to get the function 1 over 1 plus x. And on the right, we get an alternating series. Right, the minus sign gets squared away, then it shows up on the cube, and then it goes away on the fourth, and so on. That's going to be true as long as my new value I'm plugging in is inside the radius of convergence. So in other words, we need minus x to lie between 1 and negative 1. But that's no different than x being between negative 1 and 1, right? If x is between 0 and 1, minus x is between 0 and minus 1. If x is between 0 and minus 1, x is between 0 and 1. So we get the same situation. This makes sense as long as the absolute value of x is less than 1. Therefore, 1 is our radius of convergence. Okay, and so let's summarize here with a nice sigma form. We now know a power series that converges to this function. And in sigma form, we could write it, the power start at 0. So let's start our sum at 0. And then notice we get an alternating feature. It starts out positive, so I think just to the k. And then we're going to have x to the power k. And that only makes sense if x is between minus 1 and 1. Completely ridiculous outside of that interval minus 1 to 1. And for the record, it diverges at the endpoints, but we don't really care about that yet. We will in just a minute. Now, let's do what we did over there. Let's integrate. And it's a little bit less complicated here because the derivative of the inside is plus 1, not negative 1. So over here, I just get the natural log. And again, it can't be negative because x is between minus 1 and 1, so I'll write parentheses. And then I get the summation k equals 0 to infinity, minus 1 to the k, that's a constant, and then I get x to the k plus 1 divided by k plus 1. And that is true on the interval of convergence, inside the radius of convergence. So we get a power series that converges to the natural log of 1 plus x. Now there's something very interesting there. Let's, to this point, I've ignored the endpoints. You got a chance to work with those in earlier, the last video in section 2. And today, until right now, we've ignored the endpoints. But what I want to do is take a look at the endpoints here. In particular, let's look at the endpoint x equals 1. So the question is, on the endpoints, does the series converge or does it diverge? If it converges, we include that endpoint to the interval of convergence. If it diverges, then we don't. If we include it, we write a square bracket around it. If we don't, if it diverges, then we just leave the parenthesis there, okay? So at x equals 1, the series, it looks like this. Let me go up high so it won't hurt my back. I get summation k equals 0 to infinity minus 1 to the k. And we're plugging in 1, so 1 to the k plus 1. divided by k plus 1. Let's just write some terms out. When k equals 0, this is positive. This is 1. That's 1 always. So we just get 1. When k equals 1, now the minus kicks in. Minus 1 to the first. This guy is 1 always. And then we're going to divide by 1 plus 1. And then when k equals 2, back to positive. 1, third, minus, and so on. What series is that? One minus a half, plus a third, minus a quarter. We've seen it before. I think, I hope. It's the alternating harmonic series. If the signs were all plus, it's the harmonic series, and since they alternate, it's the alternating harmonic series. Now, when we use the adjective harmonic, we might think, oh, that's bad, it diverges, because we're memorizing that fact. The harmonic series diverges, but this is not the harmonic series. It's the alternating. And alternating, you know, every other term being negative, it helps the series converge. Instead of everything stacking up, maybe heading off to infinity, now there's a give and take. In fact, let's take a look at this. I don't know if you saw it earlier in Nick's videos, but we'll pretend like you didn't. So let's just take a little piece of the number line between 0 and 1, and let's track what's going on here. So think of the sequence of partial sums. The first guy we get is 1, so we'll put a big dot there. Now we add the next term on, we get a half. So we're subtracting it. So we go back to a half. The third term, the half we have here, we're going to add a third to it. That's 5/6. So notice the terms are shrinking in absolute value. So the distance we came back, when we move in the positive direction, we're going to go less. In fact, we're going to go to 5/6. And then we're going to go, you know, 5/6 take away a quarter is some number of 24ths. We'll work it out, but it's going to be smaller. We're going to go back smaller than we did here because the terms are shrinking. So we're going to go there, and then we're going to go there, and then we're going to go there, and so on. So somewhere in here, there is a value that it converges to. So the harmonic series diverges. The alternating harmonic series converges to a number between 1/2 and 1. And now we're prepared to actually find that number. So here's what we have. We just use it right where it's written. We now know that this converges, oops, inside -1 and all the way up to including +1. We just showed. Officially, this series converges by the alternating series test. Ignoring the alternating, all of the terms are positive. They go to 0 and they decrease uniformly. So it converges by the alternating series test. And using this, just analyzing the sequence of partial sums, we can figure out it's going to converge to a number between 1/2 and 1. But remember, we have a function that converges to. So now that we know it converges at 1, we can plug in 1 and we get this very interesting result. Let's write it out. We're plugging in 1. That's exactly what I did here. So 1, you just copy it over. So we get that the alternating harmonic series converges to the natural log of 2. A very interesting and important result. Alternating harmonic series converges. And now we know to the natural log of 2, which for the record is about 0.69. consistent with our analysis over there on some number between 1/2 and 1. At the other endpoint, and we're going to get -1 to the k. These guys will stack up, and it's the regular harmonic series which diverges. So we can include the right-hand endpoint, but not the left-hand. This is the interval of convergence. But the very interesting thing is that we now know what the alternating harmonic series converges to. So the ordinary harmonic series diverges. Not interesting. The alternating harmonic converges and converges to the natural log of 2. Now, some years ago, people were building calculators to save people like us from tedious calculations. And so if you're building a calculator which can do basic arithmetic operations, how do you get it to calculate logs? Well, one way to do it, the way that they did, I mean, they've modified and tweaked it and improved it over the years. But start with, just like here, I can get the log of 2 just by doing simple arithmetic. And the more terms I include over here, the more accurate it gets. Of course, to get exactly log of 2, we have to go to infinity. But just by doing simple arithmetic, addition, subtraction, division, we can get a transcendental number like the natural log of 2. And while it is more sophisticated and lots of interesting things, that's basically how your calculators work. Whatever the transcendental number is, log 2 or e or whatever it is, they find an arithmetic sequence, series that converges to it, and then they just use it. They can just use it, basic operations. You know, power series, all it is a basic arithmetic. And we're seeing that we can get lots of different kinds of numbers as a result. Let's do one more example. I want to take a look at this series. So to this point, we've been working off of the geometric power series because we knew what the function it converged to. Okay, and we did some work with it. We made some progress with it. Now I'm going to start something totally new. I want to look at this power series, and we'll see if we can figure out the function it converges to. So the sum k equals 0 to infinity, x to the k over k factorial. I'll say in advance that this is probably the most important power series of them all. And we're going to discover why. Let's write the terms out, just for the fun of it. When k equals 0, actually not for the fun of it, it's going to make it easier. X to the 0 is 1, 0 factorial surprisingly is 1. When k equals 1, we get x over 1 factorial, and then we get x squared not equals plus. Can make that prettier. I won't do any arithmetic, I'll just write out what's going on, x cubed. The factorial doesn't really do anything till here. We'll write out one more. And so on. So we're wondering, like, what function is this? Earlier in this video, I gave this very series as an example of a series, a power series for which R is infinity. That is, it converges for all x. I didn't prove it then. I'm not going to prove it now. I'll tell you that if you want to prove it, use the ratio test. And because, you know, all we have is powers, exponential functions, and factorials, the ratio test is super easy to use. And the limit will actually be 0. That is, it won't depend on x, which means it converges. 0 is less than 1. So it converges by the ratio test. And since it doesn't depend on x, it converges for all x. So I'll let you work it out. Maybe that was an example that the calculus professor used. Now, what I want to do is let's take the derivative. Just we're exploring what what in the world could this function be? Well, let's take the derivative and see if we notice any pattern. The derivative of, first I wanted to, well, it doesn't matter. The derivative of 1 is 0. This guy is just x, his derivative is 1. And now we bring the 2 down, taking the derivative, that cancels this. 2 factorial is just 2, so I get x. And then I bring the 3 down, and it cancels the 3, but the 2 times the 1 is still there. That is, I get x over 2 factorial. See that? 3 cancels. 3 factorial is, I can write as 3 times 2 factorial. You bring the 3 down and the derivative, they cancel. And then the same thing happens here. The 4's cancel. I think I skipped the, oh, I forgot to write a square there. Perfect. Then we bring the 4 down. It cancels the first factor, and I'm left with 3 factorial. And now let me get rid of the garbage there. And now take a close look. And what do you notice? So I'm going to have to pretend like you notice it. I'll help you out. We don't need that 0. This is exactly the same as that. And because they go to infinity, they're exactly the same. Well, do we know a function whose derivative is equal to itself? We do. What function is it? E to the x. Yeah. So notice because we get exactly the same power series, f of x equals f prime of x. Now, there are actually infinitely many functions whose derivatives are equal to themselves. Any constant multiple of e to the x. So which one is this? Well, notice that if we plug in 0, we get 1. So there's only one function of the form c times e to the x that when you plug in 0, for the function c e to the x, when you plug in 0, you get the number c. So for that to be 1, c has to be 1. Therefore, f of x equals e to the x. I would write an exclamation point, but there are factorials in this problem. We'll just double box it. Actually, let's write it in all its glory, and then we'll double box it. So what we've shown is that the function e to the x is the sum of the series k equals 0 to infinity x to the k over k factorial. And this is true for all x. The work we did off of the geometric series, we could only make it true between -1 and 1. But now we get convergence for all x. Before I talked about how to get a calculator to calculate transcendental numbers. Well, now we can get it using ordinary arithmetic, addition, multiplication, and their reciprocal operations, inverse operations, and we can calculate e to any number as accurate as we want. We get more accuracy by including more terms. To be exactly the right value, we need to go to infinity. Now, since it converges for all x, let's plug in one particular. What happens if we plug in 1? On the left, we get e. On the right, we get, well, 1 to the k is just 1. So we get summation k equals 0 to infinity, 1 over k factorial, which is equal to 1 plus 1 plus 1/2 plus 1/6. 3 factorial is 6 plus 1/24, and so on. It absolutely converges to the number e. Some people might take that as our definition of the number e. In calculus, probably we would use some of the work we've done earlier as our definition. But we get just a beautiful result. Now, remember, e is, what, 2.7-ish? The first 3 terms were up to 2.5. So there's not a huge contribution from these guys, but we need them all if we're going to get exactly E. But remember, factorial grows super fast. So once they start, the power kicks in, like these terms get small in a hurry. 2.5 in the first 3 terms. This is worthy of being boxed in. Every good Calc 2 student knows this without having to think about it. Again, we could write series all day long. The square root of E, a series that converges to it, we're just going to pick x to be 1/2. And then we get, let's look over here where we wrote it out term by term. I get 1 plus x, well that's 1/2, plus x squared, 1 over 2 factorial times 1/2 squared. We're squaring our x. And then 1 over 3 factorial times 1/2 cubed. And so on. There is a series that converges to the square root of E. I can pretty it up, but we don't really need to do that. It's not important. As long as we know we could do it if need be. All right, that finishes section 2. I'll post you an assignment. There's one thing in section 2 we have not yet talked about. I'll post an assignment without it. If it turns out we need it, we'll make it part of a future video. Or I'll refer you to where it's discussed in the book. As far as I can tell, the calculus professor does not have a video over the things we've talked about today, which is why we're making this one for you. In my mind, and that means in the courses that I teach, the material that we talked about today is super helpful, and therefore I want you to see it. I want you to give you a chance to understand it. I want you to work homework problems over it, and I want you to deal with it perfectly on the exam next week, which I'll give you more information about soon. So for Friday's class, you'll watch this video. There will be homework associated with it. There could also be, think about it, there probably will not be any material from the calculus professor on YouTube. We'll focus on this right here. That's what I'm thinking today. I'll let you know if I change my mind. So I'll post an assignment. I'm recording this on Thursday morning, and maybe by Thursday afternoon I could have an assignment up. This is the assignment. This video was for Friday's class, so this would be due on Monday. I've greatly reduced late penalties. I'm trying to make it easy for you to have the freedom and the time to complete the homework. And the most important thing is not that you get 100% of the points, because remember, homework's not a huge percentage of your grade. The most important thing is that you understand what you're doing and you understand why you're doing it. All right, so we'll talk to you later. Happy calculus work.